Okay, here we have a conservation of energy video and or problem, and we're looking at a firecracker. We're told that a certain amount of energy is released in the explosion of the firecracker, and the firecracker is launched into the air. And we're given the final height or a height of the firecracker as well as an upward velocity. And we need then to think about the fact that the firecracker gained gravitational potential energy. All right, so we gained gravitational potential here, and we gained energy that was in the form of kinetic, right, at our second point. And then we need to find out how much energy is unaccounted for. Okay, so let's set up for part A before we talk about part B. Okay, so in part A, we have conservation of energy. And this is going to include basically non-mechanical or non-conservative forces. So conservation of energy, we'll say generally here with non-mechanical forces. I'll say a bit more about that in a second. Okay. Okay, and so then our first step here with some conservation of energy problems is to set energy at one point equal to energy at a second point. Okay, where point 1 is at explosion. Okay, so that's just the energy of the explosion. All right, so the energy input. And point 2 is at potential energy equals mgh, and kinetic energy equals 1/2 mv squared. Okay, so then let's write the form of this, because we know we're going to expect unaccounted for energy. So here I'm going to have the energy of the explosion, so E explosion, and that's going to equal our mgh, and then plus 1/2 mv squared, and then plus E, and we'll call this not thermal, not internal, not drag, because it's everything. We're given more information in part B. So I'll just call this E remaining. Okay, and E remaining is what we're trying to solve for. Okay, so ER for remaining is going to be the energy of the explosion. All right, and then minus mgh minus 1/2 mv squared. Okay, so let's take that energy that we were given at the explosion of 643 joules. Okay, and then we'll subtract a factored out m of 125 grams, so 0.125 kilograms. All right, and then, okay, and let me just finish this line here. Okay, and then g, so 9.8 meters per second squared, times our height of 58.4 meters, and then plus, because we factored out the negative, the velocity, so 1/2, and then v squared, or 72.8 meters per second squared. So 72.8 meters per second squared. Okay, so let's go ahead and calculate that remaining energy, because that will be our value. All right, so we'll go over here. And okay, so let's do our 643 joules minus our fairly small weight of 125 grams. Okay, and then in our parentheses, we're going to have gravity and then the height. And then 0.5 multiplied by our velocity squared, 72.8, and that's going to be squared. All right. Okay, so we get 240 with 3 sig figs joules of unaccounted for energy. Okay. Okay, and part B, we're given some more information about where that energy went, and we just have to fill in the blanks. Okay, so we're told that if we assume the firecracker gained a certain amount of internal energy, okay, so I'm going to have E internal, okay, and it's going to be 5 joules. All right, and then we're also told that there is the drag force. Okay, so and all the rest of the unaccountable and unaccounted for energy went to the dissipative drag force. Okay, so then we also have the work or the energy to drag would be the work done by drag. Okay, and that's going to be the force of drag, the displacement, so h, and then cosine of 180 degrees. Okay. All right, so that's going to be the work done by drag, and then when we find that value, we should be able to solve for the average magnitude. Okay, because that's what this represents right here. In fact, we can denote it as an average, like so. And we're going to write our sum of forces here, our energy, right? So if we're going to not sum of forces, our energy conservation is going to be E1 equals E2. And just to kind of fully show what it's going to look like with the internal energy and the work done by drag, we're going to have here, we'll have U1 plus K1 plus the work by the non-conservative force, which will be drag, and that's going to equal U2 plus K2, and then plus the change in internal energy, like so. Okay. And we could also denote this NC as external sometimes by work done by an external force. Regardless, it's going to take this form no matter what you call the variables. Now, of course, in this problem, the situation is slightly different because we don't start with any potential energy, kinetic energy. So here, I'm actually going to put energy external instead, sort of to replace the potential energy and the kinetic energy. Because we're given that initial energy from the explosion. It's non-conservative, but I wouldn't write work by non-conservative force because the energy doesn't follow the format for work. We're not given a force and a displacement. We're just given energy. I mean, if we were to zoom in on the explosion, obviously there was a force that took place over some very small displacement, but it's outside the scope of the problem. Okay, so then let's write out the values in this expression. So similarly to last time, we'll start with the 643 joules. We're going to have the work from the non-conservative force. Okay, so this is going to be the average drag force. Okay, the thing we're asked to solve for. And then we're going to be multiplying by h, which we know because we were given the height that it reaches. We have the cosine of 180. Okay. So of course it's just going to become -1 right here. Okay. And then that's going to be equal to the values that we found before. So if we factor out 0.19 or 0.125 and then 9.8 meters per second squared, and then and that's kilograms, not meters here. Okay, and our 58.4 meters are 1/2 72.8 meters per second, quantity squared. And then we just have the change in internal energy, which is quite small, right? It's kind of a drop in the bucket. And it's 5 joules. Okay. All right. And I can replace this unknown h with the known value of 58.4. So we should do that since we're plugging in numbers at this step. Okay. All right. So then we simply want to solve for the drag force. All right. Okay, so here I've just wrote out the expression to solve for the drag force. So here I'm just solving for it. And let's go ahead and plug in those values. And obviously in the algebra here to set up for the drag force, I took into account the -1, right? So this -1 got pulled in the front, which is why we have a negative on the final potential and kinetic energy terms. Just like above when we were accounting for the unaccounted for energy, because this should be similar to accounting for that, is we just have to share some of that unaccounted for energy with the small internal, basically the rocket heating up as it shot up, right? Because that's increased internal energy. And then since we're not solving for a value of joules, but instead solving for force, we have to divide by distance. All right, so let's plug in our numbers here. So we're going to have, we think about it, the unaccounted, I was thinking of maybe we can use this value from above, but we'll go ahead and recalculate. Okay, so let's go to here. All right, so I can at least copy this, however, because it's got a lot of the same terms, or all of the same terms. So we'll add a 5 at the end. Okay, we have parentheses. We just need to put one at the other side. Okay. And then let's divide by 58.4. All right, so we get a drag force rounded to 3 significant figures of 4.20 newtons. All right, that's our average drag force. Now we know drag would not remain constant, but this would be its average. Okay, all right. Thank you for listening.